In this topic, we're talking about transition elements. Transition elements have very different physical properties compared to your group 1 metals. If you recall, the mnemonics I used to help you remember the physical properties of group 1 metal, the lady called Lena, I mentioned that Lena was light, okay, with a low density. However, when it comes to transition elements, right, transition elements are heavy, okay, they are the opposite of Lena. They have, number 1, high density. Next, I also mentioned that Lena, right, is a lady who cries easily, melts easily with low melting point. Well, transition elements is actually very different. It's on the other side, it's opposite or that of Lena. Transition elements, right, instead of low melting point, they have very high melting point and boiling point. So, transition elements basically have high density and high melting point and boiling point, and they're mostly metals, okay, in that chunk there. Okay, so that's why sometimes we call them transition metals. Now, there are also some chemical properties that you need to know for this chapter. Okay, and the first one is that transition metals, elements, as well as the compounds that they form. Take note, it's two things, transition metals itself and their compounds that they form are very good catalysts. Now, a catalyst is a substance that increases the speed of your reaction. Okay, increases the speed of the reaction while remaining chemically unchanged. Very important, while remaining chemically unchanged after the reaction. Okay, so I'm going to give you two examples of catalysts that you will encounter in your syllabus here doing your O-levels chemistry. The first one is actually iron. And to be very precise, right, iron is actually used in the Haber process. And to be very precise, right, iron when used in Haber process is actually in the form of a very finely divided. Okay, let me write that again. Finely divided iron, okay? In the form of a very finely divided iron, this is actually used in the Haber process. Now, when it comes to nickel, right? Nickel is also another catalyst. It is used to convert your vegetable oil to margarine. And nickel you will encounter again in the topic of organic chemistry. Now, finely divided iron, the Haber process, right? You can actually look at my video on ammonia where the Haber process is actually discussed in more details. Another chemical properties of your transition elements is that they have variable oxidation state. Now, if you recall your group 1, right? For example, your sodium. Now, sodium, right, has a group number 1. So what happens is that they form ions, okay? Sodium, okay? Form ions, which is Na+. So as a result of this, the salt that they form, for example, sodium chloride, okay, we will write this as sodium chloride. Okay, it's written as NaCl. What you really want to note is that after the word sodium, there's actually no bracket with a Roman numeral. Okay, but however, let's consider an example of one of the transition elements called chromium. Well, chromium, okay, can actually have two oxidation states. +3 it could either be +3 or +6. Now, what happens is in this case when chromium actually have an oxidation of +3, it can form and a compound called chromium chloride. Chromium bracket 3 chloride. Now, what you must take note is in this case here, because it has a variable oxidation state, as long as it is transition elements, right? When you write it in English, it is chromium, there's a bracket 3, and this number here reflects the oxidation state of your chromium. So, next, as a form of +6, right? Chromium comes out in the form of potassium dichromate bracket 6. What is interesting to know is that in this case here, your chromium appears, okay, in the behind instead of the front. Let me just zoom in more on this one, okay? So what happened in this case here, for example, your potassium dichromate, right? The formula is actually K2CR2O7. This is actually the formula. Now, you might wonder, how are we actually going to determine the oxidation state of chromium in this case here? So let me show you. So the formula is potassium dichromate, okay? K2CR2O7. That means that in this case here, it is actually made of 2 potassium and 2 potassium as well as 1 dichromate ion. We actually have this formula here. Now, when it comes to determine the oxidation state of chromium, right, we actually need to take note of whatever the oxidation state, okay, let's just zoom in here on this guy here, put this into the center. Now, the oxidation state of your chromium plus the oxidation state of your oxygen, okay, they must add up to, okay, add up to -2. Now, we know that oxidation state of oxygen is -2. It is taught in your redox chapter. We always make it as we always consider oxygen as a -2. So in this case here, because we have 7 oxygen, that means in this case here, it will be 14 times -2. This we do not know yet. Okay, is equals, okay, to -2. Now, this means, right, if you work this out backwards, you will discover that this is actually +12. And since there's actually 2 question marks here, the question marks become 12 divided by 2, which is actually the OS oxidation state of your chromium, which is equals to +6. And that is how you can determine the oxidation state of your chromium. So chromium exists in the form of oxidation state of +3 and +6. Now when it comes to manganese, right, it has 2 oxidation states as well. For manganese, it will be +4 and +7. Okay, so one of the examples I'm going to give you about manganese is your very familiar purple potassium manganate, which have the formula of your KMnO4. Now, if we were to open this up, right, is actually K plus and MnO4 minus. Now let's zoom in on this ion here. Again, we know that the oxidation state of oxygen is -2. So this means that the OS, oxidation state of your manganese, plus the oxidation state of your oxygen is equals to -1. So in this case here, because we have 4 oxygen, okay, is 4 times -2 equals to -1. So in this case here, that makes it such that your oxidation state of your manganese is actually -1 plus 8, which gives me +7. That, students, is the oxidation state of your manganese in your KMnO4. Now, with this in mind, right, the last physical properties, right, you need to know is that your transition elements form colored compounds. Now, in the case of your potassium dichromate, right, it forms, okay, for your case of your potassium dichromate, K2Cr2O7, your K2Cr2O7 is actually orange. Okay, and for your KMnO4, right, this guy here is actually purple. There are still a number of colored compounds that you can actually see for reference on your textbook, or else also as well as internet. Each time if you type transition elements and colored compounds, you actually find a lot of them. But the main principle is that you should be able to determine the oxidation state, okay, by using this method of calculation, okay, and I've here given you only 2 examples. You can look out for more, okay, in your textbook as well as in the internet. So this is the topic on transition elements. Thank you.